So now let's work on the next two problems here. First, we want to identify what part of the original molecule is still going to be there in the product. It looks like all the carbons are staying and we're not adding any new carbons. Now let's kind of analyze change to functional group. We are making an imine, which we know how to do, and we only know one way to do it. So knowing that there's only one way to get this imine, let's just start by writing down what we know we must have started with immediately prior to the imine. We would need a carbonyl compound, and we would need an NH3 and H plus acid catalyst, HOTS, or sulfuric acid. So now our question is, how do we make methyl cyclohexane, convert it into this particular ketone? Well, our methyl cyclohexane doesn't have any functionality on it, so that means that we have to start by putting some functionality on the methyl cyclohexane. So I'm going to go all the way up here. I'm going to use NBS and some light, and that is going to selectively halogenate the same carbon that has the methyl group, which is really not where we want our carbonyl to be. We want the carbonyl to be right here, right there, but that's okay. If we have a functional group on a carbon that's adjacent to where we want our functional group to be, so we've got a functional group here, but we want a functional group over here, no problem. What we want to do is eliminate. Just use a regular base because we want to make the most substituted double bond. And now we're going to add, we're going to do an addition so that we can put a functional group in the right spot on that carbon. And since we're trying to get an oxygen out there, what we want to do is use a set of reagents that will just put an OH out there in the right spot. And then we'll be able to oxidize to the ketone. So in order to get this OH group out here in that position, we want to do an anti-Markovnikov addition of water, BH3 with THF, H2O2, OH minus, and then we do oxidation. And so as we're going through this worksheet, I hope you notice that sometimes when I solve problems like this, I start at the end and work back to the beginning, which is I think what I did for this first problem up here. Sometimes I start at the front and at the beginning and just work forward. And sometimes I start at the end and then I go to the beginning and then I just kind of meet in the middle. So for our next one, let's take a look. I don't know why, but this one looks really intimidating to me. Let's take a look at the carbons that we're starting with and the carbons that we're changing. This isn't going to be too bad. We have functionality on this carbon right here, and we want our functionality on this blue carbon. We don't have to do any kind of carbon skeleton change. We just need to change functional groups and change the location of the functional groups. So our first job is, go from this. Our first job is to eliminate so that we can get a functional group onto the blue carbon. And we want to eliminate so that we create a double bond in between the red and the blue carbon. So we're looking for this particular alkene here, which is the least substituted alkene, which means that we need to use the bulky base to get the double bond in the right spot. And then once we get that double bond in the right spot, we want to introduce new functionality, putting it onto the blue carbon. And because we're trying to get an aldehyde group on there, it is going to make the most sense if we can put an OH group out there on that blue carbon. So we want something that looks like that. And once we get that OH group out there, we'll be able to oxidize this using PCC. That'll oxidize us to the aldehydes. This problem actually isn't that bad at all. CH2C, that looks so bad. CH2Cl2. So how do we get the alkene to the alcohol? Well, we can see we're doing an anti-Markovnikov addition. So again, we're going to use BH3 and THF in H2, or followed by H2O2 OH minus.